Okay, so this is the summary of the whole course. So I think for the whole course, we have spent almost 14 weeks on going through this four very important part in machine learning, including classification, regression, clustering, and dimension reduction. So this is the roadmap that that you have seen this in the first week. So this is a recap of what we already been and what we already done. So this is a quick summary of all those models, methods, theories. It's by no means the most comprehensive one, but I will try to capture as much important information as needed here. One of the very important part that that in this whole course is we need to use this kind of cross-validation idea to prevent overfittings. So as you can see right here, this is the error and the training and the validations errors. So you can use something called holdout methods that basically randomly assign this data into two parts, 80% of training, 20% of like testings. So and then the size for each set can be arbitrary, but usually this test set will be smaller. So the whole idea is we train and then we train our models on the training set and evaluate the performances on the testing set. So this is kind of like the simplest kind of cross-validation that you can think. So, and we can vary our number of parameters and redo this again, again, again. Then you got a plot of this and this and plot versus and training error and validation error versus this number of parameters. So the key here is, the model is getting more and more complicated. The training error always decreases asymptotically. However, this validation error or testing error will start to increase after certain number of the parameters. So the error start to increase gradually. So you can see from this picture here, everything in this region will be underfitting and everything in this region will be overfittings. So so there will be spot of the number of parameters right here. This will be the optimal number of parameters. Actually can minimize the validation error or testing errors. So the key here is not to minimize the training error. Training error doesn't matter here. The key is we need to make sure our model works well for those new data has never seen before. So this is k-fold holdout methods, and of course and we have a k-fold cross validations. So and this there's another one that is more complicated. It's a version of k and cross validation. It's called k-fold cross validations. So basic k-fold cross validation is the example is randomly partitioned into k equal sized subsamples, and out of k subsamples, a single sample is being trained as validations, and the remaining k minus one will be and use the training and the data. So you so then you repeat everything k times. Then each of the k subsamples will be exactly used once as the validation data. So this is kind of the very important method. And we usually set k equal to 3 or 4 or 5 such that it won't take too much time. So and the goal is and this works very well if our data is not very large. It's just a small portion of data. So we can look through and all these data and train this data very quickly. Then the k-fold cross-validation will has some benefit here. But if you are working so if you want to work with very large data set, then the k-fold cross-validations won't be good because that would take too much time. But with and if the data is really, really large, it doesn't, and necessary to work on the k-fold because those testing and training is already large enough, can fully represent the whole data set. And and the whole and the population and the distributions. All right, so that would be fine. And also we talk about a bunch of optimization methods, and this has been and discussed and used a lot in multiple in a multiple occasions. So these are the two. It's like techniques we learned in the machine learning part, cross-validation and gradient-based methods. We have a gradient descent, and we have a stochastic gradient descent and a mini-batch gradient descent. So the difference is for the gradient descent, we actually calculate the full gradient on the whole data set, and update the theta accordingly. So this is the actual and the gradient with respect to the total loss. And this one is a stochastic gradient, and it's basically we are interested in, and we are only calculating one and a gradient of the one sample point. So we are going to update that with only one sample point, right? So this is basically we update theta here. And for the mini batch is we are going to update my theta. So we partition our data set with a bunch of batches with each batch is called B, and the depth and size of B is bigger than 1, but smaller than the number of the total and the data and the number of the of n. So basically this is the batch of B here. So you calculate the gradient on this batch of B, then you update the theta accordingly. All right, so the second thing is the regression. So like we have a talk about a lot of models, including and regression and classifications. In particular, for the classification, we have been particularly left out separate modules on the neural networks. So that's a separate topics. But we're going to combine this together into the classification because the only application that we talk about or used in in this courses is just simply on the regression on the classification part. Okay, so in terms of regression, we have this training data. We have been like given these things a lot of times. So this is my training data. Xi, yi, I from 1 to the n. X is actually a vector. I is a vector in R little d. Yi is a continuous variables in R. The goal here is we want to predict the target variable y with a feature of x, which given as follows right here. So the key here is we assume this model is being w times the phi x plus some like noises here. This noise is here. We assume it's a Gaussian noise, and this noise is independent of x. Phi of x is like nonlinear, and it could be some like nonlinear transformation here. And for simplicity, if we work with the linear regressions, then this phi of x is like it, and you can just like and put everything and create your new phi right here. So basically, you have you can recreate your data matrix by putting phi and a phi x phi x1, phi x2 into the data matrices. So I mean, right here, this X matrix, it's nothing but okay. Let me just using the notebook. I think that might be easier. Just a second. Okay, so I think this is I can write it like directly on, so it will be easier. So I mean, this is all the method that we have talked about: gradient descent, stochastic gradient descent, mini batch gradient descent. Okay, so in terms of regression right here, I mean, the model, basically the model that we got is my y is equal to W transpose of phi of x plus some epsilon right here. So this is basically my epsilon is some Gaussians of mean of 0 and sigma square. And also the key here is my error is independent of x right here. And of course, there's some, and you can impose some like nonlinear transformations, so if needed. But and this is being like and discussed in detail in the kernelized regressions. So the first thing that we talk about is if you are giving such kind of features, you can just create this your new data matrix X, which is phi of x1 and the phi of x2, and so on, phi of xn. Okay, so in this one, that could be n by d. D is the dimension that needed and write down this phi of x. So if we take this nonlinear transformation, this d could be really large, right? And it could be even like bigger than n here. So the key here, if we are working with like linear regression here, the cost function is basically and the residue sum square. This w hat is actually the minimum of this like cost function, and so in this case it can be solved analytically. And but of course, I mean, we just use this like simple linear regression, it's very likely to have the problem of overfittings because you don't know how and whether the feature that you got is too many or not. I mean, it's too many, then so it will be easily overfit. So what you do is you can add some like penalty. So what I'm going to do is I'm going to introduce the penalty of the magnitude of the regression coefficient to prevent overfittings. So this is something called L2 regularization or Tikhonov like and regularization. So and what it's basically doing is I'm going to introduce the lambda of square and lambda times square of the 2 norm of the coefficient W to the like residual sum square. In this cases, we can actually still solve this W hat analytically, which is given right here. It's still like a linear and to solve a linear equation here. But for both this linear regression and ridge regression, we don't get the sparse solutions. But sometimes we want to get the sparse solutions because sparse solution can lead to feature selections. So that means like for those like and weight with the zeros, so that means these features are not important. I just can completely get rid of this. So here we are introducing something called L1 regularization. L1 regularization can lead to sparsities. So this is the very key important here. So all you need to do is just instead of and put like the 2 norm, you put in the 1 norm here. If we choose this like and a cost function right here, it will be there will be no like analytical solutions. But instead we have to solve it numerically. What you do is you use this pocketwise coordinate descent to solve this problem numerically. And you can go back to my lectures to see my derivation. And this whole thing is particularly appealing if like one of the dimension and one dimension optimization problem can be solved analytically. So what is what is the point right here is, I mean, if we fix one coordinate, so if we fix every other coordinate, let the one coordinate to move. In fact, for this problem, we can solve it as analytically. So we can use this whole idea to loop through all possible coordinate to optimize my my like W's and with the approach of pathwise coordinate descent. So at the end, you can solve this and a W hat numerically, and you can guarantee this. And this whole problem is convex, so it's very likely you can get and unique solutions. But of course, this is not, and strongly convex, you might get like multiple solutions sometimes. The point of lasso is for the feature selections, and of course, so this is still biased, but you can like debias it by performing the linear regressions with these new features if you need it. Okay, so then it's classification. We spend really a lot of time on classifications. So for classification but the difference is right here is my yi is from 1 to the c. C is the number of the class label. If c equal to 2, this is like binary classification. If C is bigger than 2, that will be multi-class classification. Here, shouldn't be called like logistic regression, should be and classifications. Okay, so the goal here is if you are giving a new data of X, I want to predict a target variable of Y. So we really talk a lot of and different method. For example, on the first, we talk about the logistic regression here. So in terms of the logistic regression, we spend a lot of time on two parts. One is perception, one is binary, and the logistic regressions. The perception here is nothing but like 0, 1 loss. So that means if this part is bigger than 0, that will be 1, and otherwise that will be 0. So we can calculate this like cost functions by taking the square and basically sum of square loss. However, this whole thing and L is not differentiable because of this 0, 1 function. It's not like, and the 0, 1 indicator function is not differentiable. So this is not really good. So what we usually what we can do here is we can so we introduce something called fake gradient, which to introduce so basically we get rid of this part, and because we don't know how to take like and the derivative with respect to phi, and then we just introduce the stochastic gradient and a gradient like descend out an algorithm to minimize my loss functions. It just turns out work. So this is the very baby version of this logistic regressions. And then what we do is we introduce something like and we have this kind of like and the logistic models here, which is a sigmoid function. So this is a sigmoid function. So this is, and this we're using this sigmoid function output to be interpreted as the probability that X belongs to the class of 1. So basically says, so this is probability Y equal to 1 given on X and W. So of course, the probability of Y equal to 0 conditional on X and W, that would be 1 minus of sigma here. Here, this is the function of the sigmoid right here. And of course, so in terms of sigmoid, the whole function will look like this. It will be, so this is the X, this is Y, the function look like this, right? So, I think I should draw it carefully. So this function will look like this. So that would be like between 0 and 1s. So if everything is like and above like half, that will be belongs to 1. Everything like below then half, that will be 0. So this actually and it give you the classification here. Okay, so the beauty of everything is if we actually just use this and a sigmoid, unlike what we have for the 0, 1 loss, this is quite smooth, and we can actually find the gradient. So analytically, we don't have the issue of the differentiabilities like what we had before. And then we calculate this loss functions. In this case, we use negative log likelihood as our loss functions. So this is equivalent as cross entropy loss. So cross entropy loss, it's equivalent with negative log likelihood in the situation of the binary and the logistic regression cases. The beauty here is we can find out the gradient analytically, then we can apply this stochastic gradient descent method. Then next, we talk about supported vector machine SVM. So in SVM, we move the intercept out and change the label from 0 to 1 to +1 and -1. There's no fundamental changes here. So basically, so the point is, and the whole thing is, and we are separate everything into, and the whole space we have, so we want to draw a line. All right, so this is a line that we want to predict. And so everything and above the line will be plus, and everything below the line will be minus. Right, so this is the whole point. So the motivation and to get an SVM is because in terms of and the logistic regressions, you might get multiple solutions, but some solutions and might not be robust enough. So the point is we want to find the best separator, and which is basically my decision boundaries, to maximize the margins. Right? So and we need to define the margin and find a way to maximize the margins, right? And of course, this only works if the data is linearly separable. If it is not, if it's not linear separable, then we can't even talk about this. So there will be supporter vectors and the margin boundary. So basically, what we do is basically on this decision boundaries, we're going to draw two margin boundaries, which is in the cases that is this value is equal to 1, and on the bottom that will be equal to 0 as -1, right? So I want all my and my positive is in this region, and all my minus is in and below of my margin boundaries, such that they can separate as much as possible. And for the point that just happen to be on this margin boundaries, that will be my support vectors. So we come up with this our constraint optimization problem. This is a hard margin, so we don't allow any kind of any misclassifications. So this is a constraint optimization, and this whole problem can be solved by and numerically with SMO algorithm. Then sometimes it's not a good idea to have that kind of strong restrictions. And what we can do is sometimes our data have outliers, all right? So it will be much nicer to relax this constraint a little bit to allow certain misclassifications for outliers. So what we do is we introduce this slack variable Cassie here, that to allow those points to move across this margin boundaries. Okay, so this is basically the distance that these points can cross this margin boundaries, which is the Cassie. So now we change our and constraint optimizations into this following look like, which is again, it's not that easy to solve. And we can find the due problem like what we did in the hard margin problems. And of course, if we set lambda to be and infinities, it will become hard margins again. So that means I don't want to allow any kind of any misclassifications. The beauty of this soft margin classification is we can rewrite these things in a different form by accommodate this and it can see of and we can accommodate these constraints, and in the meantime eliminate this Cassie completely. So this actually becomes like this. So basically this is my Cassie of I. So all we need to do is and to choose CY and equal to this term, that will be good enough. So that becomes, so this is nothing but something called hinge loss. Right, so this is basically a hinge loss plus L2 regularizations. The beauty of everything is we can find a gradient analytically, and we can use the stochastic gradient descent to minimize it. The kernel trick we also talk about quite significantly, even in the regressions here and on the classification as well. So the key point is actually to put the training data into much higher dimensional feature spaces, that the data is separable, and hopefully, and these data is linearly separable in those feature spaces. So instead of you directly work on the phi, you actually work on the kernels, which is phi xi transpose and phi of xj. So this is a size of n by n, and this is quite appealing if my d here is much bigger than n, which is the dimension of the phi here. So then basically this class and the classifier is can be written in terms of this kernel functions right here. All we need to do is just plug in the kernel to calculate this and the whole thing very efficiently. So the point is to calculate it. This kernel for one value for given I and j turns out is more efficient than just to calculate the phi of xi and the phi of xj. Then we do the inner product. So and the point is and this is more efficient. This is more efficient to calculate. Okay, so but this time this primal problem cannot be solved easily. You actually have to solve do problems, right? So this is in the the kernel trains. I briefly mentioned a little bit on the multi-class, and we have one against all and one against one schemes. This will be discussed more detailed in 593. K-nearest neighbor, I just very briefly mention about this on the first lecture. This is really simple things. It's non-parameterized algorithms. There's no training needed, and we can make a prediction directly. Use the k-nearest data samples, and with that. So the key is just that and the distance function is very expensive to calculate. We need to find a way to calculate this distance functions. So efficiently. Decision tree. Decision tree is a very popular method. It can work with regression. It can work with and the classification at the same time. And also, these features can be either continuous or category or discrete. At the same time, this dependent and which is labeled could be discrete and the continuous. If it is discrete, this will be classification. If it is continuous, that will be regression. Okay, so we can have some loss function with this. Basically, we are going to partition the whole space into a bunch of blocks. And each block that will be W1, W2, W3 by using this piecewise and a linear function to make the predictions. But there's no gradient method to approximate this loss function because everything is piecewise and piecewise continuous. So piecewise constant, that's not differentiable at all. So what we do is we're using this greedy algorithm, so that we want to iteratively grow our trees one node at one time. The key is if some feature that is highly informative, I'm going to then place higher up on the root. Higher up in a tree. So, and for example, if this feature is highly informative, it's very informative. I probably will put on the root, and then we and search the next informative feature. Then I will be put on the next and the next levels here. All right, so there are a bunch of like algorithm that we talk about. The first one is ID3, the second one is C4.5, the second and third one is CART. And we talk about the math, we talk about everything, and basically like implement everything from scratch. For ID3, it used information gain as the metric, but they only works with the categorical and the discrete features, right? So, and C4.5, it can accept discrete and continuous features, but instead you work with and highest information gain. It works with highest information gain ratio from the feature whose information gain is average or higher. So this is more complicated. So you just choose the features and the best features strategically. The last one, CART, it can work with discrete, it can work with continuous, and for the feature and the target. I mean, basically, this is the most generalized version of the algorithm. And instead of using the information gain, they're using something called Gini impurity as a metric. And also, it can only generate a binary tree. But for ID3 and a C4.5, it's not necessary to be binary tree. And for each tree, it can have multiple branches, right? But if you want to get a binary tree, you should only use the CART algorithm. Okay, so we implement everything from scratch, right? So this is the key part. Deep neural network. Okay, so now I put it back into the classifications. So deep neural network, and we talk about this like input layers and basically has 3 different type of layers: input layers and output layer. If we don't have the hidden layers, that basically becomes the multi-class and the logistic regressions. If we have an input layer, hidden layers, and output layers, then this becomes a deep and a neural network. If we have more than one hidden layers, this is a deep neural network. The output layer, that will be a vector, so you can treat this as a predicted probability for the K classes if we use the softmax on the output layers. So there are a lot of an activation function that we can choose: sigmoid, ReLU, hyperbolic tangent. Softmax only be applied on the output layers, right? And you can use various different and the loss functions. You can do mix and match. So like, and the logistic and the loss is preferred, and we talk about why why the logistic loss is preferred, but you can still work with the square loss if you need it. There's nothing against to it. The most difficult part in the deep neural network is how to create compute this gradient efficiently, right? So right here, we have a forward, we have a backward. Forward propagation, we have a backward propagations. We have a span of really, and quite amount of time to derive the forward propagation, to derive the backward and the propagations, and implement everything from scratch. So after that, and we use this forward and backward propagations to calculate the gradient for each layers from 1 to the L. So we can calculate this sample error and partial sample error, partial the WL, and partial sample error CI with respect to the bias factor BL here. So everything here is like implemented from scratch. So the reason this is called forward propagation is because this L is from 1 to the capital L. Is from left to right. So this is called forward. And the reason that it's called backward propagation is it start with L minus 1, L minus 1, L minus 2, and until we got 1. So this is actually being calculated from right to left. So that's why this is called backward propagation. All right, so that's everything for the classification. We also spend really long time, I think a couple, 3 weeks on the clustering as well. So this is and also a very main topic, but like, I mean, so right here, this is unsupervised learning. So that means we no longer have the labels anymore. So the key here is we have this unlabeled and the data example x of I, and we specify the number of the cluster and the partition of K. Then basically we group the examples into K clusters. So basically A of xi belongs to cluster 1, cluster 2, and to the cluster of K. Okay, so in K-means, the goal is we want to find a K cluster, C1 to Ck, and their corresponding centroid, mu1, mu2 to mu-K, that minimize the total within cluster variances. So this cost function is given as follows, is called distortion. Here, this like xi belongs to the cluster of Cj. So this is assigned to the cluster that with the closest centroid. So so that would be the Cj right here. And that's how we make the prediction right here as well. So I mean, so basically we go through all possible mu1 to mu-K and calculate the distance between as xi to mu1 to mu-K, and find out which one is the closest centroid that will be, I mean, the cluster that xi will be signed up to. There are multiple like for loops and in the calculation of the cost. So that's why to make your code to be efficient, it's extremely important when implementing K-means. So the method that we use is called the LOID an algorithm, which is alternative like optimization methods to minimize the cost function. And later on, we have shown this is a special case of EM algorithm. Then the second model we talk about in clustering is Gaussian mixture models. So in Gaussian mixture models is we assume this data is generated in two-step process. The first step is to generate the cluster membership. That means this Zi belongs to 1 to K for any like and from 1 to K with some multinomial distributions pi 1 to pi K. And the second, like, given this and the cluster Zi equal to the cluster C, then we generate x of I from this and associate and the multivariate Gaussian distributions, which is with a mean of mu C and the covariance of sigma C. Okay, so this is basically the Gaussian distribution part. The goal here is to infer these parameters from our training data. So these parameters will be this multinomial distributions pi from pi 1 to pi K, and the mu1 to mu K, and the sigma 1 to sigma K. These are the parameters that we want to infer. At the end, I want to recover the cluster, which is so the member of clusters for each data. I mean, in this case, this will be Z1 to Zn. So these are like the latent variables that we don't actually observe that. So we want to use our algorithm to recover this and a cluster. So like naturally, this becomes like clustering algorithms. So the loss function that we are going to use is the log likelihood functions for Gaussian mixtures log likelihood. But you can see right here, I mean, this whole thing is quite difficult to minimize. And so in particular, to find the gradient of the log likelihood with this parameter, it's a very difficult problem. I mean, it's a difficult process. So that's why we and we introduce something called EM algorithm. EM is called expectation maximization algorithm, to actually maximize the log likelihood functions. So we also talk about why EM will work, and what is the detailed steps by step for EM algorithms. We didn't talk about hidden Markov model. This is being usually talked about in stochastic process courses. So at last, we talk about so very briefly on the dimension and the reduction, which is the fourth part of this course. So in general, for the dimension reduction, this is to learn a mapping from high dimensional value and high dimensional spaces from RD into low dimensional latent spaces of Z. So basically this latent space Z is not observed. So what we actually observe is data in R big D. So, and the only method that we discuss about is the principal component analysis. So the key is we want to find a proper projection onto the D-dimensional subspace with orthonormal basis W1 to WD. These W1 to WD are orthonormal. So basically, and the W1 I and WJ. So in the product of Wi and Wj, if I is not equal to j equal to 0, the norm of Wj is equal to 1. So the key here is we want to solve this an optimization problem. So this optimization problem is called it's we find, and we're trying to find the orthonormal basis of this subspace of V by solving this and maximum variances problem. You can think about, we basically projected the covariance matrix in the direction of Wj, and we're going to sum of all the variance component from the contribution from W1 to WD. But with the constraint of orthonormal constraints. So this is a quadratic and objective functions. But my constraint is very difficult. My constraint is actually a non-convex constraint. So this whole thing becomes a non-convex problem. It's generally very, very difficult to solve. But fortunately for this specific problem, and so this can be solved so analytically, and which is Wj equal to Vj right here. So this is the first D columns of my V, and V here is my singular value decompositions of my X matrix. Right, so this is very few situation that you can actually solve non-convex as optimization problems by just simply assign the W1 star to WD star equal to V1 to VD, and V they are all and corresponding singular vectors and the left singular vectors of the data matrix X. But of course, we need to make assumption here. So I forgot this, and we need to assume X has a 0 mean, right? So this is the assumption before you process any kind of PCA here. So zero, X has, it doesn't have a 0 mean, then you have to subtract the mean here to make sure shift to an origin here. All right, so low dimensional data and the representation. So we have and even though we project everything into and with and the basis of and the V1 to VD, so it is still and using capital D coordinate to represent that. So the intrinsic low dimensional data representation is we are going to just using the weight to represent this data. So this is being and represent by Zi. Zi is and a lower dimensional representation of X of I. So this is nothing but VD transpose times of Xi here. So if we do this an operation, this is nothing but you got this data is intrinsically in R small d. Then with collection of this Zi, you can stack them together. Then you can feed in them. into the pipeline of your classification algorithms. So you can work on SVM and various different methods if you want. So the reason that it's good to work on like much smaller and a dimension is because it will like save you a lot of time, and it can even make your performance and algorithm performance better. Okay, so that's everything about the summary of all the code and the material we have been talking about. We go back to the first one. So this is basically these full picture. We have a classification here. We have a clustering here. So this is like regression. And this is dimension reductions. Okay. So we spend the most time right here on the classification and the regressions. I think 2/3 of time. And the rest, or 1/3 of time, we talk and a little bit on the clustering on the dimension reductions. Okay, so this is basically everything I want to talk about for the whole course. There will be one more lecture on LDA. I will briefly mention about this. This is basically the combination on the classification and the dimension reductions. So we combine both of that. This will be something called LDA here. All right, so that's everything for the summary.